Every digital device, from the simplest calculator to the most powerful supercomputer, rests on a foundation both invisible and indispensable: its architecture. Computer architecture is the blueprint that defines how the components of a computing system are organized and how they communicate, shaping both capability and performance. Understanding this architecture is essential not only for engineers and designers, but for anyone seeking to grasp how modern technology operates at its core. The landscape of computer architecture is shaped by decades of innovation, from the earliest mechanical calculating machines to today's complex, interconnected processors. Each advance has brought new ways of solving problems, managing data, and pushing the boundaries of what machines can achieve. By exploring the structure and function of computers from the ground up, we can appreciate how these systems transform raw data into meaningful action, and why their underlying design matters in our digital world. Imagine a world without computers. Our daily routines would be transformed, scientific progress would stall, and communication would slow to a crawl. Yet the power and ubiquity of modern computers rest on foundations built over centuries, with each careful design decision shaping the next. At the heart of this evolution lies the discipline known as computer architecture, a field that determines not only how computers are constructed, but also how they function, interact, and ultimately serve us. Computer architecture can be thought of as the blueprint for building and operating computers. It defines the structure of a computer system, describing how its component parts, hardware, software, and everything in between work together. This structure can be considered at several levels, from the overall organizational plan down to the precise logic and instruction sets that guide the machine's actions. Whether we are discussing a pocket-sized smartphone or a sprawling data center, all computers are built upon these architectural principles, which specify how hardware and software connect, how instructions are processed, and how data flows through the system. To appreciate the significance of computer architecture, it helps to look back at its historical roots. The first documented ideas about computer structure can be traced to the correspondence between Charles Babbage and Ada Lovelace in the 19th century. Babbage's analytical engine was a marvel of mechanical design, and Lovelace, in her notes, anticipated concepts that would later become central to programming and architecture. Fast forward to the 20th century, and the landscape begins to change dramatically. In 1936, Konrad Zuse described the stored program concept, an idea that would become a linchpin of modern computing. The 1940s saw a flurry of activity. John von Neumann's 1945 paper outlined the logical organization of a computer, introducing what would later be known as the von Neumann architecture. Alan Turing, whose own work cited von Neumann, was also shaping the theoretical underpinnings of computation. The term architecture, in the context of computing, did not appear until the late 1950s during IBM's Stretch project. Frederick P. Brooks, Jr., a pivotal figure in that project, defined architecture as the art of determining the needs of the user of a structure and then designing to meet those needs as effectively as possible within economic and technological constraints. This definition highlights a crucial aspect of computer architecture. It is not just about technical specifications, but about balancing user requirements, performance, and the limits of current technology. The evolution of computer architecture mirrors the evolution of the computer itself. Early milestones include George Stivitz's relay-based adder in 1937, Konrad Zuse's Z2 and Z3 computers in the late 1930s and early 1940s, and the Atanasoff Berry computer, completed in 1942. During World War II, the British bomb played a critical role in code breaking. These achievements marked the transition from mechanical to electronic computing, paving the way for more sophisticated machines. At its core, computer architecture defines how a computer's components communicate using electronic signals to perform three essential operations: input, processing, and output. Every digital computer, regardless of its era or purpose, is composed of several basic building blocks. These include the central processing unit, or central processing unit, memory, input and output devices, and the pathways, known as buses, that connect them. Let's take a closer look at each of these pillars. The central processing unit, often called the brain of the computer, is responsible for executing instructions and managing the flow of data. Within the central processing unit are distinct subcomponents: the control unit, which directs operations; the arithmetic logic unit, or arithmetic logic unit, which handles mathematical and logical calculations; and registers, which provide quick access storage for immediate data. Modern central processing units may also include cache memory to speed up access to frequently used information, and many have multiple cores, allowing them to process several tasks in parallel. Memory is another critical component, serving as the workspace for data and instructions. This includes random access memory or random access memory, which temporarily stores information that the central processing unit needs to access quickly, as well as more permanent forms of memory like read-only memory and secondary storage devices such as hard drives or solid-state drives. The memory unit ensures that data can be stored, retrieved, and manipulated efficiently. Input and output devices form the bridge between the computer and the outside world. Input devices such as keyboards, mice, and scanners allow users to provide data and instructions. Output devices, including monitors and printers, present the results of a computer's operations in a human-readable form. The interaction between these devices and the central processing unit is managed by the bus system, a network of electronic pathways that carry control signals and data throughout the machine. The relationships among these components are captured in what is often called a block diagram of a computer. In this diagram, data flows from input devices to the central processing unit, where it is processed, then to memory for storage or retrieval, and finally to output devices for presentation. The bus system ties everything together, ensuring that information moves smoothly and efficiently. Over time, different approaches to organizing these components have emerged. The von Neumann architecture, for example, describes a system in which program instructions and data share the same memory space, a model that remains influential today. Other designs, such as the Harvard architecture, separate instruction and data memory, which can offer performance advantages in certain contexts. Taxonomies like Flynn's categorize computers based on how they handle instructions and data streams, reflecting the diversity of architectural solutions. Advancements in computer architecture have far-reaching consequences. The efficiency, reliability, scalability, and even the security of modern computing systems depend on these foundational choices. Innovations such as microprogramming, developed by Maurice Wilkes during the Electronic Delay Storage Automatic Calculator project, have enabled more flexible and powerful machines. Today, the demands of artificial intelligence, cloud computing, and the expanding Internet of Things all rely on robust architectural designs. Throughout history, the field has benefited from the contributions of visionaries like Ada Lovelace, Charles Babbage, Alan Turing, Conrad Zuse, and Grace Hopper, each adding new layers of understanding and capability. The journey from early mechanical calculators, like the ancient abacus, to the sophisticated digital computers of today is a testament to the enduring importance of architecture in computing. In summary, computer architecture provides the blueprint for all modern computers, defining how hardware and software interact and how data is processed from input to output. It is a field shaped by historical innovation and grounded in the careful balancing of user needs, technological possibilities, and practical constraints. As we look ahead to the next wave of computing, from quantum processors to intelligent machines, the principles of computer architecture will remain as vital as ever, guiding the design and function of the systems upon which the world increasingly depends. Imagine, for a moment, the humming interior of a modern computer. At its center lies a component so essential that its very name, Central Processing Unit, reveals its significance. The Central Processing Unit is not just a chip nestled on a circuit board. It is the beating heart of computation, the orchestrator that transforms code into action. Decades ago, the Central Processing Unit was a formidable cabinet, a single box within a room-sized machine. Today, it is a minuscule yet astonishingly complex package, soldered onto a motherboard and embodying the concentrated power of billions of transistors. Whenever you open a spreadsheet, stream a video, or send a message, it is the Central Processing Unit that interprets your instructions. It does this by executing the steps of a computer program, arithmetic, logic, control, and even input and output, all within the blink of an eye. The Central Processing Unit's internal structure is a marvel of design, consisting of three principal components: the Arithmetic Logic Unit, or ALU, the registers, and the Control Unit. Each plays a distinct but interconnected role in the grand process of computation. Let us begin with the ALU, the Arithmetic Logic Unit. This is the workhorse of the Central Processing Unit, responsible for carrying out mathematical operations, addition, subtraction, multiplication, as well as logical comparisons like and, or, and not. The ALU is where numbers are added, conditions are checked, and decisions are made. In modern processors, there may be several ALUs working in parallel, each handling separate calculations. This parallelism allows for remarkable speed, enabling the Central Processing Unit to process multiple instructions or parts of instructions simultaneously. But the ALU does not work alone. It relies on registers, tiny, lightning-fast storage locations that temporarily hold data, instructions, or addresses. Registers serve as the Central Processing Unit's internal scratchpad. For example, when the ALU needs to add two numbers, those numbers are first loaded into registers. The result is then stored in another register, ready for the next operation. Some registers are general purpose, used for a variety of tasks, while others have specialized roles. 4 registers are especially vital to the central processing unit's operation. The program counter, or PC, keeps track of the address of the next instruction to be executed. The instruction register, or IR, holds the current instruction fetched from memory. The memory address register, or MAR, stores the address in memory that the central processing unit wants to read from or write to. The memory data register, or MDR, is where data read from memory is kept, or where data to be written to memory is staged. These registers work together, ensuring the central processing unit knows what to do, where to find its data, and where to store the results. At the helm of all this activity is the control unit. The control unit acts as the director, providing timing and control signals to every part of the processor. It determines which instructions to fetch, how to decode them, and how to execute them. It tells the ALU when to perform an operation, signals the registers to load or store data, and manages communication with memory and input and output devices. The control unit also keeps everything running in sync with the system clock, ensuring that each step of every instruction happens in the correct order and at the proper moment. The process by which the central processing unit carries out its work is called the instruction cycle, sometimes referred to as the fetch, decode, execute cycle. This cycle unfolds billions of times each second inside your computer. First, the control unit fetches the next instruction from memory using the address stored in the program counter. This instruction is then loaded into the instruction register. The control unit decodes the instruction, determining what needs to be done. Does it require an addition, a comparison, a jump to a new memory location? If the instruction involves data in memory, the memory address register and memory data register handle the flow of data between memory and the central processing unit. Finally, the ALU executes the instruction, with the results stored in the appropriate register or written back to memory. The program counter is updated and the cycle repeats. A crucial aspect of the CPU's operation is its instruction set, the collection of basic operations it understands. This is known as the instruction set architecture, or ISA. The ISA defines the vocabulary of the CPU, the set of commands, the format of instructions, and the way data is addressed and manipulated. The choice of instruction set influences everything from how quickly a CPU can execute programs to how efficiently those programs are written. Not all instruction sets are created equal, and over time, 2 major philosophies have emerged, RISC and C. RISC stands for Reduced Instruction Set Computer. In this approach, the instruction set is kept small and simple, with each instruction designed to be executed swiftly, often in a single clock cycle. The simplicity of RISC instructions allows for high execution speed and greater efficiency. This design is especially favored in mobile and embedded systems where power and speed are at a premium. CISC, or Complex Instruction Set Computer, takes a different approach. Here, the instruction set is broad, with many complex commands that can perform multiple operations in a single instruction. CISC processors can accomplish tasks with fewer lines of code, making programming simpler in some respects. However, complex instructions may take several clock cycles to execute, and optimizing for speed becomes a more intricate challenge. CISC architectures are common in personal computers, especially those using the x86 family of processors. The performance of a CPU depends on several intertwined factors: how many instructions a program requires, how many clock cycles each instruction takes, and the speed of the system clock itself. The clock cycle is the heartbeat of the CPU. 1 tick of the clock equals 1 step in the instruction cycle. Modern CPUs operate at staggering speeds with billions of clock cycles each second. However, clock speed alone does not determine performance. Architecture, generation, and features such as multi-core designs, caches, and parallel execution all play critical roles. Today's CPUs are feats of engineering, often containing multiple processing cores on a single chip, each capable of running separate threads of execution. They devote substantial space to caches, tiny but extremely fast memory banks that keep frequently used data close at hand. Some CPUs even integrate memory and peripheral controls, particularly in microcontrollers and systems on a chip, providing a compact and efficient platform for a wide range of technologies. At its core, though, the CPU remains true to its purpose: to fetch, decode, and execute instructions that bring software to life. Whether built for speed or complexity, simplicity or versatility, the processor stands as the heart of the computer, tirelessly translating ideas into action, one instruction cycle at a time. Imagine data in a computer as a traveler moving through a vast and intricate landscape, guided by invisible rules of speed, access, and necessity. At the heart of this landscape lies the memory hierarchy, a carefully engineered structure that determines how swiftly and efficiently information can be fetched, manipulated, and stored. The organization of memory is not random or arbitrary. It is shaped by the principle of locality of reference. This principle suggests that programs tend to access a relatively small portion of memory repeatedly over short periods, whether that be specific instructions or chunks of data. By taking advantage of this predictable behavior, computer architects have designed a hierarchy where each level balances speed, cost, and capacity to minimize access time and maximize overall system performance. The journey begins at the very top, with registers. These are the smallest and fastest memory locations, found directly within the processor itself. Because registers are so close to the central processing unit's core, data can be retrieved from them almost instantaneously. In practical terms, this means that the most critical pieces of information, numbers to be added, addresses of the next instruction, or temporary results, are always within easy reach for the processor's immediate use. The sheer speed of registers, however, comes at a cost. They are few in number, and their total storage capacity is minuscule compared to other forms of memory. Just below registers sits cache memory. Cache acts as a bridge between the blistering speed of registers and the more leisurely pace of main memory. Organized in multiple levels, often labeled Level 1, Level 2, and Level 3 in modern systems, cache holds a subset of data and instructions that the processor is most likely to need next. Its design ensures that blocks of information at higher levels map to specific, limited positions at lower levels, which helps optimize both speed and efficiency. The result is a system in which the most frequently or recently accessed data are kept as close as possible to the processor, dramatically reducing the time required for repetitive tasks. The next major stop in the hierarchy is main memory, typically referred to as random access memory. While main memory is far more spacious than either registers or cache, it is also markedly slower. Here, the computer stores all the data and instructions that are actively in use, but not quite urgent enough to merit a place in the cache. Whenever the processor needs information that is not already cached, it must reach out to main memory, a step that takes more time, but is still vastly quicker than turning to storage devices located further down the hierarchy. Further along the path, we encounter secondary storage, the realm of magnetic disks and optical disks. These storage forms are vast and comparatively inexpensive, capable of holding immense volumes of data, everything from operating systems to high-definition videos and sprawling databases. Yet speed is not their strong suit. Accessing data from these devices is orders of magnitude slower than from main memory. In fact, before the processor can even use information stored in secondary memory, that information must first be loaded into main memory. This extra step introduces additional delay, but it is a necessary trade-off for the ability to store large collections of data permanently and at low cost. The hierarchy does not end here. Some systems also employ auxiliary and external memories, such as solid-state drives, universal serial bus devices, and additional forms of optical media, extending the landscape even further. Each level in this memory pyramid is distinguished by its own mix of speed, cost, and capacity, and each is optimized for a specific role within the computer's daily operations. A crucial element binding all these levels together is the computer's bus system. Picture the bus as a set of highways, each carrying a different kind of cargo across the computer's internal terrain. There are several main types of buses, each with its own responsibilities. The address bus, for example, is a one-way street, transmitting memory location information from the processor to memory. It tells the system where to send or retrieve data, but it does not carry the data itself. The data bus, by contrast, is a two-way route, shuttling actual data and instructions back and forth between components. Then there is the control bus, which communicates vital signals that coordinate when and how data moves, ensuring that all parts stay in sync. The width of these buses, that is, how many bits they can carry at once, has a direct impact on system performance. Wider buses allow more data to be transferred in a single operation, increasing bandwidth and reducing bottlenecks. Buses are not limited to just central processing unit and memory. They also connect internal peripherals via local buses and external devices through peripheral buses. Modern designs use both parallel and serial communication methods, and often include features like direct memory access, or DMA, which allows certain hardware subsystems to transfer data independently of the central processing unit, boosting efficiency for large, repetitive transfers. All this careful orchestration is not merely for show. The performance of the memory system is shaped by factors like peak and effective data rates, the maximum possible speed of data transfer, and the speed actually achieved under real-world conditions. System overheads, such as waiting for buses to become available or the time needed to switch between data transfers, mean that effective rates are often lower than the theoretical peak. The organization of memory, then, is a story of constant trade-offs and optimizations. Each memory location, whether in a register, the cache, or main memory, has a unique address, and the whole system is structured to allow efficient access to the right location at the right time. Memory units are built from registers, each a tiny storage cell, and the management of these units involves intricate schemes for allocation, virtual memory, and cache management. These strategies are designed to make the most effective use of limited resources, ensuring that the processor spends as little time waiting as possible. As you consider the arc of data moving through a computer, from the innermost registers out to sprawling external drives, remember that this hierarchy underpins the speed and responsiveness of every digital device. The invisible choreography of memory and data flow is what transforms raw hardware into a seamless, responsive machine, capable of meeting the demands of everything from simple calculations to the most complex simulations. In this way, the memory hierarchy stands as one of the quiet triumphs of computer architecture, a layered, adaptive system that keeps the engine of modern computing running smoothly. Imagine sitting at a computer, typing a message or clicking a mouse. Each action feels almost instantaneous. A letter appears on your screen, a window opens, a song plays through your headphones. Yet beneath this seamless experience lies a sophisticated choreography that enables the central system to communicate with the wide array of devices we call peripherals. This intricate dance is managed by the input-output subsystem, or simply the input-output system, which forms the bridge between the digital world inside a computer and the external world of users and devices. At the heart of this connection is the input-output subsystem, a collection of hardware and software components designed to move data between the computer's internal circuits and external devices. These external devices, known as peripheral devices, greatly expand a computer's capabilities. They include keyboards, mice, printers, external drives, routers, and more specialized equipment. Peripherals connect to the main system through various means, such as wired connections like universal serial bus, high-definition multimedia interface, and Ethernet, as well as wireless technologies like Bluetooth and Wi-Fi. Each connection extends the computer's abilities, enabling interaction, storage, communication, and control far beyond what the central processing unit and memory can achieve alone. However, the journey data takes between a computer and its peripherals is more complex than it might seem. Each device often operates at a different speed with its own data format and communication protocol. To manage this complexity, computers use input-output interfaces, specialized circuits or chips that serve as translators and mediators. These interfaces handle the details of transferring information between internal storage, such as memory, and external peripherals, smoothing over the differences in how each side operates. Communication between the central processor and these devices happens through buses, sets of wires that connect the various components. The system bus serves as the primary pathway, allowing the central processing unit to communicate with memory and peripherals alike. This bus is typically shared by many devices, so its bandwidth, the amount of data it can carry at once, is crucial for overall system performance and reliability. Within the broader input-output subsystem, you will also find components like disk controllers, disk drives, tape drives, and other specialized input-output devices, all using the system bus to send and receive information. When the host computer wants to communicate with an input-output device, messages are usually broadcast across the bus, reaching all connected peripherals. Devices send messages back to the host when they need to report status or transfer data. This arrangement requires careful coordination to prevent confusion and ensure that data reaches the correct destination at the right time. Managing this flow of information is a shared responsibility between hardware and the operating system. The operating system coordinates with input-output devices to ensure smooth operation, handling device control, configuration, data transfer, storage, and support for new or unfamiliar peripherals. It acts as a conductor, directing the system on when and how to communicate with each device, and managing the nuances of data formats and transfer protocols. At the center of this orchestration are several techniques for managing input-output operations, each with its own advantages and trade-offs. The simplest method is polling. In polling, the central processing unit acts as a vigilant supervisor, continually checking each device's status to see if it needs attention or has data ready to exchange. While straightforward and easy to implement, Polling has a significant drawback. It keeps the central processing unit busy with repetitive checks, using processing cycles that could be spent elsewhere. This makes polling suitable for simple or low-traffic devices, but inefficient for systems handling many peripherals or high data rates. A more efficient approach is interrupt-driven input-output. Instead of constantly checking each device, the central processing unit focuses on its primary tasks until a device signals interrupts the processor to indicate it needs service. When an interrupt occurs, the central processing unit temporarily halts its current activity, saves its state, and responds to the device's request. This mechanism allows the computer to react quickly and efficiently to input and output events, greatly reducing the time spent waiting or checking device status. Interrupt-driven input and output conserves central processing unit resources and lowers the delay between a device's request and the system's response. For larger, sustained data transfers, such as copying a file from a hard drive to memory or streaming video to a display, systems often use direct memory access, or DMA. Direct memory access is a powerful technique that allows specific hardware subsystems, called DMA controllers, to transfer data directly between memory and peripherals without involving the central processing unit in each step. Acting like a traffic controller, the DMA controller manages the details of moving data, freeing the central processing unit for other tasks and reducing system latency. Direct memory access is especially valuable for high-speed devices like network cards, graphics cards, and storage controllers, where large blocks of data need to move quickly and efficiently. Direct memory access can be implemented in different ways. In polling-based direct memory access, the central processing unit still checks the status of the DMA controller to know when a transfer is complete. This approach is simple but keeps the central processing unit somewhat involved, limiting efficiency gains. More advanced is interrupt-driven direct memory access, where the DMA controller signals the central processing unit via an interrupt when the transfer is finished. This hands-off method minimizes central processing unit overhead and further improves performance, making it ideal for demanding applications. To further relieve the central processing unit and streamline data movement, some systems use dedicated input and output processors. These specialized chips or subsystems manage the flow of data between peripherals and the main processor. By communicating over the system bus or through dedicated DMA channels, input and output processors can handle complex or high-volume transfers, offload routine data management from the central processing unit, and improve overall system throughput. The integration of peripherals into modern computer systems is constantly evolving. Connections that once relied on bulky cables and proprietary standards are now increasingly unified through interfaces like PCI Peripheral Component Interconnect, which allows peripherals to be plugged directly inside the computer close to the central processing unit for high-speed communication. The expansion and versatility of computers owe much to this flexibility. Each new device, whether wired or wireless, extends the machine's power and utility. Underlying all these mechanisms is the fundamental goal of the input and output subsystem, to provide reliable, efficient, and flexible communication between the computer's central system and the external environment. The choice of input and output technique, polling, interrupts, direct memory access, or dedicated input and output processors, reflects a careful balance between simplicity, performance, and resource use. As computers continue to evolve and their interactions with the world grow more complex, the input and output subsystem remains a vital, dynamic frontier, quietly ensuring that every keystroke, click, and data stream reaches its intended destination. Imagine standing at the edge of a bustling city, watching as new skyscrapers rise, roads are reconfigured, and neighborhoods transform overnight. The world of computer architecture is much like this, ever-evolving city, dynamic, purposeful, and shaped by the pressures and opportunities of its time. As we look ahead, the central question in computer architecture is no longer just about making things faster or smaller. Instead, it is about discovering smarter, more efficient ways to handle the data, hungry, energy-sensitive, and increasingly complex workloads that define our digital era. The story of current trends in computer architecture centers on parallelism and specialization. For decades, performance gains came from increasing clock speeds, but that approach has reached both practical and physical limits. Now, the focus has shifted to multi-core and many-core processors, chips that contain several or even dozens of independent processing units on a single piece of silicon. This shift has been transformative, allowing computers to tackle multiple tasks simultaneously and enabling the immense data processing required by modern applications. However, this new landscape brings its own set of challenges. Software must be designed to leverage parallel hardware, requiring new programming models and careful balancing to maintain cache coherency and avoid bottlenecks. The complexity of multi-threaded programming means that while hardware is ready to move forward, software often struggles to keep up. Specialization is another defining trend. Rather than building one-size-fits-all processors, architects are designing chips tailored to specific domains. Domain-specific hardware such as graphics processing units, tensor processing units, and neural processing units has become increasingly common, especially in fields like artificial intelligence and machine learning. These specialized accelerators can perform targeted tasks with remarkable speed and energy efficiency, often surpassing general-purpose central processing units for select workloads. As artificial intelligence and big data continue to grow in importance, researchers are exploring even more customized architectures, pushing the boundaries of what hardware can achieve. Heterogeneous computing is gaining momentum as a way to harness the strengths of diverse processor types within a single system. By combining central processing units, graphics processing units, and other accelerators, architects can dynamically assign tasks to the most suitable hardware, improving both performance and energy efficiency. This approach is especially valuable as workloads become more varied. Chiplet-based designs, where multiple smaller chips are linked together to function as a single unit, have also emerged as a promising way to scale performance and flexibility without the manufacturing challenges of building ever larger monolithic chips. Energy efficiency has become a strategic imperative. The explosive growth of data centers, artificial intelligence workloads, and cryptocurrency mining has made the energy demands of computing unsustainable if left unchecked. Architects are now measured not just by raw performance, but by how much work a system can accomplish per watt of power consumed. Efforts to maximize efficiency include memory-centric designs, where memory access patterns are optimized to reduce unnecessary energy use, and system-level optimizations that consider the entire computing environment. At the forefront, optical and photonic technologies are being explored as potential solutions for high-speed, low-energy computing. Light-based computation, such as photonic quantum computers and optical neuromorphic hardware, promises massive parallelism and exceptional energy efficiency, especially for tasks like artificial intelligence inference. The move toward edge computing introduces further complexity. Processing data closer to where it is generated, whether in a smart sensor, an autonomous vehicle, or a factory robot, can reduce latency and bandwidth usage, but it also demands hardware that is robust, energy efficient, and capable of adapting to unpredictable workloads. Designing architectures for the edge means grappling with constraints that simply do not exist in the controlled environment of a data center. Security is another area where architectural innovation is being put to the test. As systems become more interconnected and attacks more sophisticated, hardware-level security features are becoming essential. Domain-specific hardware can enable secure computation in sensitive environments, while open instruction sets offer greater transparency and flexibility for organizations seeking to customize and audit their systems. Agile chip development practices, which allow for faster prototyping and iteration, are helping researchers and industry respond quickly to emerging threats and requirements. The role of software architecture is evolving alongside these hardware advances. Microservices, event-driven systems, serverless computing, and edge-based solutions are reshaping how applications are built and deployed. Data and artificial intelligence are now central to architectural decisions, and large language models are becoming increasingly prevalent in both research and industry. As software becomes more distributed and adaptive, it places new demands on hardware, requiring architects to anticipate and support emerging patterns of computation and communication. This interplay between hardware and software is fueling a wave of innovation that extends beyond traditional boundaries. Cell-based architectures, privacy-focused engineering, and green software initiatives are all part of a broader movement towards systems that are not only powerful and scalable, but also responsible and sustainable. Researchers are exploring new paradigms for evaluating and benchmarking architectures, recognizing that existing simulation frameworks and analytic methods are often insufficient for the complexity of today's systems. There is a growing awareness that supporting robust research infrastructure is critical to sustaining innovation. Looking even further ahead, quantum computing and light-based processing represent areas of keen interest and rapid development. While practical applications for quantum computers are just beginning to emerge, the potential for parallelism and speed is extraordinary. At the same time, advances in optical technologies, such as chip-scale microcombs and wavelength division multiplexing, are enabling new forms of neuromorphic computing that could revolutionize artificial intelligence workloads with unprecedented speed and energy savings. Despite these exciting developments, significant challenges remain. Scaling architectures to handle ever larger and more diverse workloads, developing effective techniques for simulation and validation, and ensuring reliability and security are ongoing concerns. The intricacies of parallel programming, the need for energy-aware design, and the pressure to deliver systems that are both flexible and robust all demand sustained research and creativity. In this landscape of rapid change, one thing is clear: computer architecture is more vibrant and essential than ever. The field continues to shape and be shaped by the technologies and demands of the day, blending deep technical ingenuity with a keen awareness of practical constraints. As new directions unfold, whether through the rise of domain-specific accelerators, the adoption of heterogeneous and memory-centric systems, the integration of artificial intelligence-driven design, or the pursuit of quantum and optical breakthroughs, computer architects are at the forefront of building the future. For those who study and engage with this discipline, the journey is far from over. In fact, it may be just beginning.